Hi, today we're going to continue talking about the Bohr model because we're not quite done yet. Instead of getting into a do now where we answer questions, I thought it would be a good idea to maybe just do a brief review of what we saw yesterday. So the process is written there where this absorption occurs where energy comes into the atom in the form of light or heat or maybe electricity. And then the electron jumps away from the nucleus to a higher energy state. After some time, the electron falls back down, and then this emission is always in the form of light. This cycle actually happens fairly quickly on the order of nanoseconds, which is why when you saw the sample burning, it just seems to have a constant color. If we had a really quick camera, maybe we would see some individual light particles, otherwise known as photons, being emitted from the atom. But because this all does get mushed together and because you have several atoms in your sample, and usually the sample is being provided a large amount of energy and a range of energies, what we'll end up seeing is that you'll see these several colors coming out at once and your eye mixes them together, but if we were to get a prism out, we would see individual bright lines. I also wanted to say that like this picture on the top shows one way to represent these energy transitions where this hidden y-axis is increasing energy, so this is low and this is high. But also the Bohr model draws the atom as a nucleus surrounded by several different tracks or shells where electrons can exist. Remember that the idea behind the Bohr model was when we have a spectrum and it only has a few lines, that is to say that the transitions that happen in the middle that would create those colors of light that you're not seeing can't happen. So Bohr really established this idea that there are fixed energy levels and fixed locations for electrons to be, and then other locations where it can't be, and those energies aren't seen. So this is just showing the emission spectrum that we would see through a prism on the top, and then on the bottom you would see several different colors of light from hydrogen as these different transitions, having their different energies, different wavelengths of light, and different distances of jumps, are all happening constantly, simultaneously, repeatedly with different atoms. However, that's not the only transitions that happen. The ones that I just saw on the previous slide are what we call the Balmer series. These are each named for a different scientist. And the Balmer series involve transitions where electrons fall from specific energy levels to specific energy levels, namely from energy levels above the second level to the second level. Bohr decided to label these with number n, or with the letter n and numbers counting from 1. So first energy level, second energy level is n equals 1 and 2. But there are other transitions that exist. Here's the Lyman series and the Paschen series. Paskin? Not sure. But you can see by these nanometer numbers for the wavelength of light and the spectrum that I included, that the Lyman series has numbers that are way lower than our visible light, closer to ultraviolet, and this Paschen series, Paskin, exists well above infrared. So it's not necessarily super helpful to only go by the visible spectra that we see, because there are a bunch of other transitions that can occur, and we want to give some credence to those. So we have to talk about how else we can represent these transitions that get away from just talking about colors of light and instead might get into just talking about the electrons as they can potentially move. This is where we enter into a discussion of shell notation, otherwise known as Bohr notation, or building Bohr atoms. On your periodic table, the numbers in the bottom left underneath the atomic number are called an electron configuration, and this is giving you a map for drawing these Bohr atoms. You may not have the protons and neutrons listed in your atom. You can. So you might see a nucleus listed as a dot, or you sometimes might see the number of protons, and we're going to go with the most common isotope, rounding that to the nearest whole number, so you have 6 protons and 6 neutrons. Don't forget that we do have a reference table. You can use that link to pull up a copy and read along. Hope that didn't mess up the QR code. And then what we start building is consecutive electron shells around, oh, forgive my circles, consecutive electron shells around your atom. And then these numbers here are for each energy level going on. So what we see here is 2-4. That's not a subtraction. And all that tells me is to put electrons in the first energy level, second energy level, third, and those are the relative numbers. So 2 electrons in the first energy level and 4 electrons in the second. And we don't really provide any more form than that. We just kind of put dots. So I'm just drawing some dots here. So we should be able to translate between these Bohr atoms with these very poorly drawn circles and the electron configurations relatively easily. This yields a wonderful two things that are worth note. First, why, when I have 6 electrons, did I not just put 6 electrons in the first energy level? And that is because, due to some things we have yet to talk about, there is a maximum capacity for each energy level. If we're going to use n to represent the energy level, so first, second, third, fourth, and etc., the capacity for that energy level can be calculated by 2n squared. So I'm going to make a list just to make sure everyone has the right information. If we have our energy levels, the maximum capacities are 2, 8, 18, and 36. These numbers should be reflected on your reference table. If you look at any of the heavier, the larger atoms, you will see that the number of electrons in those energy levels as they're listed do not go larger than this number. The one thing I'm going to mention, and I should totally have included a picture here, is that there are some elements that have an electron configuration that starts with -18 on our periodic table, and then it continues. This is because the periodic table only has so much space. And there's a little star at the bottom of the periodic table that says when that happens, there's a deleted 2-8 that you kind of need to insert into that space. So it's not starting with 18, they're just deleting those inner 2 rows because there are so many occupied shells of electrons that there's just no room to write it all on the periodic table. So putting this all together, we can start talking about what an excited Bohr atom looks like. And I'm going to see something. Can I draw shapes? I don't think I can draw shapes. I should have drawn shapes, but that's fine. So if the excitation of an electron or the absorption of energy happens, electrons move up in energy levels, move to a higher energy level. We should reflect that in this electron configuration. So at this point, I probably think it's worth saying is that what is on the periodic table by like how they've built it is always the ground state. So you can kind of insert that in there mentally. 2-4 is the lowest states, which is consistent with what we saw before. The first energy level holds 2, the second holds 8, but carbon as an atom only has 6 electrons, so the first 2 go in the first, and the second 4 go in the second. But if there's any sort of excitation of your atom, what should happen is that an electron from a lower energy level jumps to a higher energy level. Which one? Well, like we saw in our previous images, all types of excitation are possible. And so we could totally just move one out of the second energy level into the third, and that would leave us with an excited atom that looks like this. Well, we can build an electron configuration for this excited atom. This one would be 2-4. This one we just have to count would be 2, 3, 1. So it's very possible to build several possible excited state configurations for carbon or for any element just by moving an electron or moving a number to a higher energy level. Technically, we could have unoccupied empty energy levels on our ground state or any other state for that matter. Usually we don't include those redundant empty shells, but you should understand that they always exist, and so you should be mindful that it could happen. Just as another example of a way that you can draw an excited Bohr atom, remember that we could build our nucleus and we've got 3 shells. You could even take an electron from the first energy level and move it up to the third, and that would look like 1, 4, 1. You could have an electron state where it's 2, 3, 0, 1, maybe if an electron jumps from the second to the fourth. There's many that are possible. And so to sum things up, just a couple of quick rules with this. Drawing an electron configuration is possible, drawing a Bohr atom is possible, and in the ground state, just use the number from the periodic table. And for any of the excited states, the only rules you need to follow are don't change the total number of electrons from what you started with, and don't overfill any shells, and don't write the ground state. So 2, 4 is really like your only impossible excited state for carbon, but there are several excited states beside that one. Thanks for watching.